Hello everybody and welcome to a presentation on learning robot trajectories subject to kinematic joint constraints. My name is Jonas Kiemel and this work was done together with Thorsten Kröger at Karlsruhe Institute of Technology. First of all, I want to explain how learning of robot trajectories usually works. In the center, you can see a neural network which is invoked at regular intervals, for instance every 50 milliseconds. The network receives as input the current position, velocity and acceleration of each robot joint, as well as additional task-specific information. It outputs parameters that define the following time step of the trajectory. Using reinforcement learning, the neural network is trained to generate trajectories that maximize a task-specific reward function. Training a neural network usually works best when all input and output values are normalized, which means that they should be between -1 and 1. In this video, we present an action space that considers the kinematic limitations of robot joints. More precisely, it ensures that position, velocity, acceleration and jerk limits are never violated. But why should we learn robot trajectories at all? An important point is that generating trajectories with a neural network is very fast, since no additional planning phase is needed. The time required to predict the next trajectory time step is nearly constant, which allows an immediate reaction to changing input values. By adjusting the reward function, the trajectories can be optimized as needed, for example to minimize energy consumption or execution time. Moreover, the trajectories are already time parameterized. In contrast, motion planners often search only for a path without considering the impact of the time parameterization. Finally, sensory feedback can be easily incorporated in order to learn control tasks. The following videos show some exemplary learning tasks trained using our approach. The two industrial robots in this rendering are trained to reach as many randomly placed target points as possible. The level of difficulty can be further increased with 3 robots. For this task, the timing of the trajectories is crucial to prevent collisions between the robots. The same technique has also been applied to the humanoid robot Armor 6 in order to learn the mutual coordination of both robot arms. The task can be made more complicated by sampling target points for both robot arms simultaneously. It is also possible to adapt trajectories using sensory feedback. In this example, a neural network is trained to keep the ball close to its initial position while following a reference trajectory. The ball position is measured by a resistive touch panel. The problem we address in our work is that all generated motions must adhere to kinematic joint constraints, regardless of what the neural network predicts. It is important to note that the limits must be respected at all times and that conflicting constraints must be prevented. A look at the website of the robot manufacturer Franka Emeka shows that compliance with kinematic limits is defined as a necessary condition for robot trajectories. Further down, the actual limits for each robot joint are specified. In some cases, it might be useful to specify more restrictive limits than those provided by the manufacturer. Position limits can be used to control the workspace of the robot. The velocity limits have impact on the speed of the motions. Acceleration limits indirectly influence the motor torques, and the jerk limits can be further reduced to increase the smoothness of the trajectory. The prediction frequency of the neural network should also be adjustable, as it influences the computational effort and the learning performance. In previous work, various action space representations have been proposed, for instance, target joint positions, target joint velocities, or target motor torques. Kinematic joint limits are often ignored or avoided by adding penalties to the reward function. However, reward shaping does not provide explicit safety guarantees and does not prevent violations at the beginning of the training process. Another approach is to search for the closest action to the network prediction that does not violate constraints. This can be done by solving an optimization problem with explicit inequality constraints. However, due to conflicting constraints, the existence of a valid solution is not guaranteed. With our approach, the neural network predicts one scalar in the range of -1 to 1 per robot joint. The network prediction is linearly mapped onto the range of safe accelerations. As a first step, the range of safe accelerations at the beginning of the following time step is computed. This range is visualized by a red line. A network prediction of -1 would be mapped to the lower end of the red line. In our example, the prediction is +1, which means that the upper end of the red line is considered as the acceleration setpoint, which is shown in blue. The same procedure is repeated for all other joints and all following time steps. The effectiveness of our approach is demonstrated by generating motions with a random agent. It can be seen that the kinematic constraints are never violated. The green lines represent the range of safe accelerations. Velocity and position setpoints are computed by integrating the acceleration setpoints. If the maximum acceleration is selected at each decision step, the robot will eventually reach the maximum position at a velocity of 0. However, oscillations may arise when the maximum position is reached between two decision steps. We suppress these oscillations by ensuring that the maximum position is reached at a discrete decision step. The basic idea to compute the range of safe accelerations is explained based on position constraints. When selecting the highest valid acceleration, the robot joint should eventually reach its maximum position at a velocity of 0. The resulting system of equations can be solved for the desired acceleration if the acceleration profile is known. The acceleration profile can be derived step by step. The maximum acceleration should be followed by the strongest possible deceleration. However, the spot marked with the red arrow must not be between two decision steps. The second acceleration profile can be used, but might lead to oscillations. The oscillations can be avoided if the maximum position is reached at the next discrete decision step. Once again, the spot marked with the red arrow must not be between two decision steps. In the final acceleration profile, the desired acceleration is marked by an orange cross. Further details, including all required equations, can be found in the document mentioned below. We compare our approach with reward shaping by learning to maximize the absolute velocity of each joint. The optimal strategy is to move back and forth between the minimum and the maximum joint position. With our approach, the generated trajectory almost equals the optimal solution without violating joint constraints. Using soft penalties, the average velocity is significantly lower and joint limit violations are not entirely prevented. With hard penalties, the number of constraint violations is even higher. The influence of the prediction frequency is shown based on a ball and play task. When executing trajectories without adaptations, the ball quickly leaves its initial position. A neural network trained at a prediction frequency of 20 Hz managed to keep the ball close to its initial spot. Increasing the prediction frequency has two effects. Firstly, the computational effort is increased. Secondly, the performance drops. If the frequency is too high, the trajectory controller can no longer follow the predicted Z points accurately. In contrast, if the frequency is too low, the time between decision steps is too high to keep the ball under control. At a prediction frequency of 20 Hz, the computational effort is low enough for real-time execution. If the frequency is reduced to 10 Hz, it is even possible to perform online collision and torque checks. If you are interested in using the presented approach for your own projects, have a look at our source code on GitHub. We also provide a Python package that can be easily installed via pip, and you can run some examples directly in Google Colab. You might also be interested in our Safe Motions package, which allows learning of collision-free and torque-limited trajectories. The code can be run on your local machine, or you can open a notebook with pre-trained neural networks in Colab and render videos of the generated episodes. I hope you enjoyed our video. Thanks for watching and feel free to contact me if you have any questions.